NASA's Juno discovers mysterious new plasma waves over Jupiter's North Pole. Astronomers have made a groundbreaking discovery over Jupiter's North Pole, revealing unusual activity that could revolutionize our understanding of plasma physics. NASA's Juno spacecraft has identified a novel type of plasma wave in its observations of the gas giant, challenging long-held beliefs about how particles behave within Jupiter's formidable magnetic field. These peculiar plasma waves were detected in Jupiter's magnetosphere, showcasing a new plasma behavior that has left astronomers puzzled as they attempt to reconcile these findings with existing theoretical models. Since its launch in 2016, NASA's Juno spacecraft has been diligently gathering extensive data and images of Jupiter, along with its moons and rings. As the mission progressed, the spacecraft's orbit gradually shifted to focus on Jupiter's North Pole, providing the Juno team with an unprecedented perspective of the planet's high-latitude magnetosphere. Jupiter's intriguing magnetosphere. Jupiter's magnetosphere is a fascinating aspect of this colossal planet, acting as a protective bubble formed by its powerful magnetic field interacting with the solar wind. This magnetosphere stretches nearly to the orbit of Saturn, reaching about 7 million kilometers toward the Sun, making it the largest magnetosphere of any planet in our solar system. This unique characteristic makes Jupiter an ideal subject for astronomical studies. Unusual plasma behavior. During their observations, the Juno team quickly noted that the plasma behaviors they were witnessing did not conform to established expectations. This unexpected finding is detailed in a recent study led by Robert Lysak from the University of Minnesota, which proposes a new theory to explain these unusual waveforms. The insights gained from this research could potentially transform how scientists model magnetic fields and related astrophysical phenomena, extending beyond Jupiter to other celestial bodies. Over nearly a decade, Juno has orbited Jupiter, collecting invaluable data about the planet and its moons. As Jupiter's orbit gradually precessed, Juno began to make closer passes to the northern pole, where it detected a low-density region in the magnetosphere characterized by extremely low electron concentrations. In these regions, where magnetic fields can reach up to 20 Gauss, 2 metric tons, an anomaly was observed. Juno's data indicated that plasma frequencies were significantly lower than the ion gyro frequency, which is contrary to the typical relationship seen in plasma physics. Under these exceptional conditions, alphane waves, which are usually linked to ion oscillations, exhibited characteristics of Langmuir waves, typically associated with electron oscillations. This unusual, hybrid phenomenon, as described by Lysak's team, is now referred to as the Alfvén-Langmuir mode. A potential paradigm shift in plasma physics? Traditional plasma physics suggests that Langmuir waves oscillate parallel to magnetic field lines at frequencies exceeding the ion gyro frequency. In contrast, Alfvén waves oscillate perpendicular to these lines and are believed to operate only below this threshold. However, the waves observed by Juno seem to have broken this rule, achieving frequencies that, while still below the ion gyro frequency, approached plasma frequencies without exceeding them. The implications of Juno's findings could indicate a fundamental change in our understanding of plasma behavior under conditions of extreme magnetization and low density. Lysak and his colleagues began to investigate the relationship between wave frequency and wave number in Jupiter's magnetosphere, leading them to propose that in this unique environment, Alfvén waves might transform into Langmuir waves at high wave numbers. The team theorizes that this unusual transformation could be driven by upward propagating electron beams with energies ranging from 1 keV to 2 MeV. Notably, similar phenomena have been observed by Juno during its previous approaches to Jupiter's polar regions nearly a decade ago. Broader implications for astrophysics. The identification of this new, hybrid, wave mode opens the door to potential breakthroughs in plasma physics, particularly in modeling the behavior of magnetospheres beyond Jupiter. The research team also speculates that similar conditions may exist around magnetized stars or exoplanets with intrinsic magnetic fields, suggesting that their findings could enhance our understanding of astrophysical phenomena in distant regions of the universe. The team's research paper, titled New Plasma Regime in Jupiter's Auroral Zones, by R. L. Lysak and colleagues, was published in Physical Review Letters on July 16, 2025. Micah Hanks, the editor-in-chief and co-founder of The Debrief, can be contacted via email at micah@thedebrief.org. You can follow his work at micahhanks.com and on X at micahhanks. Unusual plasma waves discovered at Jupiter's North Pole. Juno mission insights. What if the universe is hiding secrets in plain sight? Consider Jupiter's North Pole, where a decades-long mission has just unveiled a cosmic puzzle that challenges our understanding of plasma physics. As NASA's Juno spacecraft winds down its journey, its shifting orbit has led to a startling discovery: mysterious plasma waves behaving in ways that defy textbook theory. But here's where it gets controversial: these waves don't follow the rules we thought we knew. Could this mean our textbooks are missing something? Let's dive into the details, and why this matters for everything from alien worlds to star systems light-years away. For nearly a decade, Juno has been our eyes and ears on Jupiter, peering into its storms, magnetic field, and the chaotic dance of charged particles that surround it. Recently, the probe's orbit has tilted toward the gas giant's North Pole, revealing an anomaly: plasma waves that oscillate in a pattern scientists hadn't predicted. Researchers led by Robert Lysak from the University of Minnesota have now published a groundbreaking explanation for this phenomenon, suggesting a new way to model planetary magnetospheres and explore plasma behavior in extreme environments. 1. To understand why this matters, let's break down the basics. In typical plasma physics, electrons create Langmuir waves that vibrate along magnetic field lines at a specific frequency, higher than the spin rate of ions, their gyrofrequency. Meanwhile, ions form Alfvén waves that wiggle perpendicular to those field lines, with a frequency cap tied to their gyrofrequency. But the waves Juno detected near Jupiter's North Pole broke this pattern. Instead of hitting the expected frequency limits, Alfvén waves extended only to the plasma frequency, which was lower than the ion gyrofrequency. And here's the kicker: these waves never went beyond that threshold. This is the part most people miss, says Lysak. It's not just a minor tweak, it's a whole new category of plasma behavior. So how do we explain it? Lysak's team proposed a mechanism where Alfvén and Langmuir waves merge under specific conditions in Jupiter's magnetosphere, a region of low-density plasma bombarded by high-energy electron beams, 1 keV to 2 MeV. These beams, first spotted in 2016, might act as the spark that transitions one wave type into another at extreme wave numbers. The implications? This could help us study magnetic fields on exoplanets or magnetized stars, where similar plasma dynamics might be at play. But let's pause for a moment. If Jupiter's magnetosphere is rewriting the rules, what does that say about our current models of space weather or even fusion energy research? Could this discovery hint at hidden complexities in other planetary systems? We'd love to hear your thoughts. Do you think this challenges our existing theories, or just fills a gap? Share your take in the comments below. Rachel Berkowitz. Rachel Berkowitz is a corresponding editor for Physics Magazine, https://physics.aps.org, based in Vancouver, Canada. References. 1. R. L. Lysak et al., New Plasma Regime in Jupiter's Auroral Zones, Phys. Reverend Let. 135, 0352012025, http://dx.doi.org/10.1103/FN63-QMB7. Discovering a new type of plasma wave near Jupiter's poles. Astronomers uncover a completely new type of plasma wave above Jupiter's North Pole. Since its arrival in Jupiter's orbit in 2016, NASA's Juno spacecraft has been diligently working to reveal the numerous enigmas of the largest planet in our solar system. Its most recent finding could be one of the most fascinating to date: a brand new type of plasma wave located near the poles of Jupiter. In a study published on Wednesday in the journal Physical Review Letters, scientists detail an extraordinary pattern of plasma waves within Jupiter's magnetosphere, which acts as a magnetic shield protecting the planet from harmful external radiation. The remarkably strong magnetic field of Jupiter seems to be causing two distinct types of plasmas to oscillate together, resulting in a unique flow of charged particles and atoms in the polar regions of the planet. Plasma plays a crucial role in shaping the chaotic atmosphere of Jupiter. Consequently, the researchers believe that these new observations will enhance our understanding not only of Jupiter's meteorological phenomena but also of the magnetic characteristics of far-off exoplanets. For their research, the team examined the dynamics of plasma waves in Jupiter's magnetosphere, which contains highly magnetized, low-density plasma. This collaborative effort involved researchers from the University of Minnesota, the University of Iowa, and the Southwest Research Institute in Texas. They discovered an unexpected interaction between Alfvén waves and Langmuir waves, which correspond to the movement of the plasma's atoms and the movement of the electrons within the plasma, respectively. Typically, electrons are significantly lighter than charged atoms, which means that these two types of waves usually oscillate at vastly different frequencies. However, this was not the case in Jupiter's magnetosphere, prompting the researchers to investigate further. Their exploration led to the discovery of a previously unseen type of plasma oscillation near the poles of Jupiter. John Leif Jorgensen, a planetary scientist at the Technical University of Denmark who was not part of the study, remarked to New Scientist, "The plasma properties observed are truly unusual and have not been found elsewhere in our solar system." In contrast to Earth's auroras, which are triggered by solar storms, Jupiter's auroras, composed of energetic particles that are hundreds of times more powerful than those on Earth, can sometimes arise from its formidable magnetic field. Understanding how these phenomena function could provide valuable insights for future missions aimed at discovering extraterrestrial life on exoplanets, according to the authors of the study. The researchers noted, while such conditions do not occur on Earth, they may be present in the polar regions of other giant planets and possibly in strongly magnetized exoplanets or stars. Scott Bolton, Juno's principal investigator, stated, "Jupiter is the Rosetta Stone of our solar system. Juno is our emissary, sent to interpret what Jupiter has to reveal." Initially, NASA planned for Juno's mission to conclude in 2017, at which point the spacecraft would be intentionally directed into Jupiter's atmosphere, in accordance with NASA's planetary protection protocols. However, as Juno's flight path evolved, NASA determined that the spacecraft no longer posed a risk to Jupiter's moons, leading to mission extensions being authorized. Despite this, scientists anticipate that by September of this year, Juno's orbit will naturally deteriorate, resulting in the spacecraft being consumed by Jupiter's atmosphere. Nevertheless, this does not signify the end of humanity's exploration of Jupiter. The Europa Clipper mission is scheduled to arrive at Europa, one of Jupiter's moons, in 2030. Even after Juno is engulfed by Jupiter, researchers will still have a wealth of invaluable data from the spacecraft to analyze for many years to come.